Hi Calculus student, this video is for 5.3 part 1, Fundamental Theorem of Calculus. So finally we come to the place where we prove the fundamental theorem of calculus. The last leg here is the mean value theorem for integral. You must have heard mean value theorem before. Is saying that the slope of a secant line on a closed interval can be achieved by the derivative of a particular c in the open interval. So it is similar to that in that we're going to talk about mean value theorem for integral. Why do we need this? It is the last theorem that we would use to prove the fundamental theorem of calculus. And why do we need to prove it? Because we want to find definite integral. We want to find AB, to find AB f of x. So right now, after our goal is to find this, which is a sum of area or sided area under the curve. And right now we only know a few methods like limits, right? Of Riemann sum or geometric formula if it is a nice curve. So for anything that is a weird shape, we really do not have much hope. Or they are not polynomial, then it is very difficult. So we would need the fundamental theorem of calculus to evaluate AB f of x dx. And the last theorem that we depend on is the mean value theorem of integral. So what does it tell us? It tells us that, do you recognize this? We talk about this in 5.2. This is the average of a function value. Average of f of x. So you do an integral AB f of x. You divide it by b minus a. And it's called average. So the mean value theorem of integral says that there's guarantee a c such that f of c would actually equal to this sided area's average. Or you can rewrite it as f of integral ab f of x, the sided area under f of x, is equal to b minus a multiplied by a particular f of c. So let's, to prove it, we use the extreme value theorem, which is guarantee that if f of x is continuous over a closed interval, you can find there is a absolute maximum and minimum. Okay, and it's continuous also. Then there is a maximum and minimum. So if you're interested, you can look at how this is proved in the book. But let's just apply it and understand that, oh, it works. So we have a formula, we have a function x squared, and I want to do, from 0 to 3, the area under the curve of x squared from 0 to 3. And somehow, previously, someone has calculated for us that this is 9. They probably do a Riemann sum limit because this is not a circle or a triangle or a trapezoid. So they did that and it is equal to 9. Now, want to find c such that it is equal to the average value of this over 0, 3. So that means I will need to do, I already have 0, 3, x squared equal to 9. So what is the average value? So the average value would be 1 over b minus a, 3 minus 0. And then this number, this integral, which is x squared dx. That should be a dx here. And so that would be 9, because it's given to us as 9. 9 over 3, that is equal to 3. And the theorem, the MVT for integral, guarantee that the f of c equal to 3 must have a solution. So what is f? F of x squared. F is the number, the function that is inside x equal to 3. Can I solve it? Yes. X is equal to plus and minus square root 3. And one of them is plus 3 over, in the intervals, 0, 3. And you can say that c equal to root 3 is in this interval of 0, 3. So it validates the mean value theorem for integral. Let's do another one. But this time, I want to use another function, not x squared. I want to do a integral 0, 3, but 6 minus 2x is a linear function, so I can actually find the integral by geometric formula. So there is a question like that in the 5.3 worksheet. So I thought maybe I'll do one so to show you, because the first example you actually know. Someone gives you the integral already. So let's see. I need to calculate from 0 to 3 the integral so that I can find average value. 6 minus 2x dx. Do you want to do Riemann sum? I don't want to do Riemann sum, because it's really long. So let's just use geometric formula. Graph it. Okay, so when I graph it, I have 6 here, and I down to 1, 1. So it's a graph like that. So let's find the y-intercept here. What's the y-intercept? The y-intercept is 0 equal to 6 minus 2x. Oh, x is equal to 3. So actually from 0 to 3 is this is our area. So this integral become, because if you graph it, this is 3, and we are doing the integral from 0 to 3, meaning this is my area. So, and this is just a triangle. The triangle would be 1/2 base is 3, height is 6. So that is equal to 9 also. So this is how you do an integral using a geometric formula, because it's a line. If it's a line, you can figure out how to do it, either triangle or trapezoid or something. Now we want to find f of c so that it is equal to the average of this. So I'll set up the equation. F of c should equal to 1 minus b minus a, 1 minus 0, and this number 0, 3, 6 minus 2x dx. This we used the formula to calculate earlier. We used the area to calculate, that's 9. So f of c would be 6 minus 2x would equal to 9 over 3. That means 6 minus 2x is equal to 3. This is the average value, and I should be able to find f of c that is equal to the average area. So solve it. So 6 minus 3, so it'll be 3 equal to 2x. X is equal to 3 over 2. And it is in the interval of 0, 3. So MVT of integral apply. So this is just showing you that how MVT of integral works. So then the next thing is to prove the fundamental theorem of calculus part 1. Now part 1 is not particularly useful in helping us to find AB f of x dx, so we'll go over this really quickly, and then we'll go to part 2, which actually after 5.1, 5.2, 5.3 afterward we will actually be able to calculate AB f of x dx without Riemann sum, without geometric formula. So what is part 1? Part 1 say if f of x is a continuous function over AB, and I define big F of x. Now this big F of x is, you can think of it as the antiderivative, but it is not. It is a accumulating area function, meaning I start from somewhere under f of x. I'm going to do the area from A up to a random point x. It can vary. And so this variable area is my function. And then I do a derivative. I want to know how my area is changing. It turns out that the area is changing in a array that is f of x inside. F of x inside. So this was the derivative, and this is the antiderivative. So the antiderivative actually can be used to model the change of area under the curve. So if you look at this, I told you earlier that AX, if I have AB is a area, is a number. But if I write A and X, it become a function, right? It become a function. So this function basically is like this. F of X is just a line. Above it, it could be sided. And then you have A. But then this function changes. So if you say you plug in AX equal to 5, then you go from A to 5. You plug in x equal to 2, then it will be from A to 2. That means it depends on what your x is, and this would be your area. Does that make sense? Because whenever we write A something, it is an area. So this is x. So if x move back, a lower number, you would have a smaller area. If you have x that is move in the front, you have a bigger area. So it's a function. F of x is a function of area. And then what we're saying is, if I do a derivative of x, of this f of x, I want to know how this rate of change of the area change. It turns out that if you do a derivative, the derivative of this function area is just the function small f of x here. It's exactly how this f of x is changing, or is exactly equal to f of x. So the proof would be, I'm going to not talk about it here. The proof would be in the textbook. So let me show you the textbooks. This is the fundamental theorem. No, this is part 1. This is part 2. Part 1 is here. Fundamental theorem of calculus part 1. So here it shows you they use you want to do a derivative of f prime of x, you do a limit, right? So just from the first principle, and then somehow they do the properties of integral to change it into x plus h. And then they use Mean-value theorem of integral to prove that it is equal to f of x. So if you're interested, you can read 5.3. The proof is there. So let's get back to, after we finish proving it, what do we do? So we would say there is a function from a to anything. So now this a can be any number, but it has to be a fixed number. And then if I do a derivative, what would it be? So derivative of something that is an area that is always changing, that means it's just the inside is 1 over x squared plus 1. This is the rate function. Okay, this is it. This is very easy. So if this is dx and you have integral x, you can think of it this way. You can think of integral and antiderivative are opposite. So when you are doing a integral and then a derivative, you cancel them. These things cancel, the constants cancel, and you change your variable back to x, and that's it. So do the same thing. Oh, this x and this x cancel the integral and the derivative, change it to x. So my answer would be the rate of change of the area is sine 4x. Okay, it's actually equal to that function. No need to do plus c. So what about if this doesn't match? So if I want to do the derivative of this, so d dx 1x squared cosine t dt. In the past, this x and this x match, but now I have x and then this is x squared. So what do? I do chain rule. So I'll do d du, but change x squared to u so that it match. And then I still have cosine, but this would be cosine u, right? Cosine t dt. But after you do the integral, it will be cosine u. And then I do du dt. What is u? U is x squared. So that means this is just cosine u, which is, what is it? What is u? U equal to x squared. So just replace this by x squared, and then you do a derivative of x squared. Oh, I should say dx of x squared. So that means equal to cosine x squared times 2x. Chain rule, you just do du dt at the end. So what about this? If I have 2x and I want to do ddx, because earlier I always have a constant here, right? So 2x and then 3x t cubed dt. What do? I will split this into two parts. I will split this into 2x to a t cubed dt plus a to 3t, properties of integral, and then no, 3x, it's not 3t, and then t cubed dt. So I don't have enough space here to continue, but the idea would be like that, and I'll make sure that I'll talk about this in class. So basically you would switch this around to a negative, right? It will be a 2x t3 dt plus a 3x t3 dt, and then apply chain rule. That means you would it would be equal to, maybe I'll use some space here, just finish it. Oh yeah, I don't think I have enough time. So do it in